Ben Cohn. Today we're going to talk about polar coordinates. And we're going to talk a little bit about double integrals as well. I really don't want to, but you kind of have to have a small introduction to double integrals to understand where these polar coordinates and integration are coming from. So the reason for this is with XY coordinates, you can really do a single integral, but it's kind of tough under normal circumstances to do a single integral when you're talking about polar coordinates. You kind of get tied up in this. You'll see. Okay, so let's start with a reasonably straightforward example. So we have y equals 1/2 x, and we want to find the area under the curve. And I know you're thinking, it's like, is this that hard? No, it's not that hard. But the goal here is not to be difficult. It's here to be illustrative. Come on, line. Ooh, there's a line. Now let's change this to, get rid of that line. I will do a line like so. And down. And we'll do a copy paste. Nice. Make it straight. There we go. I'm good. I'm happy with that. Maybe we'll do one more line, like so, but we'll add a little emphasis here by making it red and a little bit bigger. Ooh, there we go. Put 1 point there, 1 point here, and we'll say that this line equals 1/2 x. Y equals 1/2 x. And we'll say this point right down here is 2, 0. This point over here is 1, 0, 1. There we go. And if you haven't figured it out yet, this is the x-axis, and then this will be the y. Okay, now I will, let's see here, lock all this into place. Whoop. That will be easy to write over and erase, except for that one dot. Darn you, dot. Okay. So when we would solve this, we would do something along the lines of, well, you wouldn't necessarily get your cyan pen out, but you might. We'd do, let's see, we have y equals 1/2 x, so we'd do an integral, like so, where this will be delta x, right? Delta x, and we will do a Riemann sum like this. So we'll move our delta x over. And then we'll do f of x right here. This will be f of x. And we'll integrate from 0, because that's x initial, to x final, which will be 2. So it'll be 0 to 2. So then f of x, so we'll do 0 to 1/2 x dx equals x squared over 2. But we already have enough 1/2 there, 0 to 2. So we have 4 over 4, which is 1. And this should be pretty standard by this point. So to kind of check this, we have a triangle that's 2 by 1. So an area of a triangle is 1/2 base times height, which in this case is 1/2 times 2 times 1, which equals 1. Does that equal 1? It does equal 1. Okay? Let's see. I don't need this. Whoop. And so it makes sense that when we found the area under the curve, we had 1. So we really didn't have to use the integral there, but we wanted to just to show how impressive we were and show off for the world. Okay? So now, to be a little bit even fancier, if you will, we're going to solve this with a double integral. So before, our entire concept was, all right, we have delta x, which is small, and we have f of x. Well, this time, instead, we're going to do delta x, delta y. And we're going to make a whole bunch of boxes going this way. And then after we have those boxes, we will then stack a whole bunch of boxes going up this way. And so we'll fill the whole thing up with small delta x, delta y boxes, as opposed to delta x wide with f of x tall. And the way we'll do that then is we will integrate, we'll start from left to right, and we'll do dx, and then we'll do dy. And you can switch these limits of integration pretty much whenever you like. So the idea here is you think of these kind of like parentheses. If I was more clever, I would write them in different colors. There we go. Think of them as parentheses. Start with the inside, work your way out. And you could switch them over, so it would be dy first, then dx next. You can pretty much always do that. You do have to be careful of things like discontinuities or when something equals infinity. But as long as you don't have that, if everything is kind of standard, then you could switch it. We could go in the y direction first and then in the x. So what we're going to have to worry about then is our limits of integration. So back to purple. So we'll do from an x initial to x final. Makes sense. We'll start here. We'll go this way. And then we'll do a little brief cyan, y initial to y final. And we'll just do the middle part first, and then we'll be left with the outer part, and then we'll do the outer part. Green? Nope, been avoiding green. Okay. Hope I don't hurt green's feelings. Okay, so we have the integral dx, and I just converted dx, the delta x to dy. I know it's an abusive notation, but it helps me visualize things. It's easier for me to see delta x and look at a graph and be like, oh, it's a small piece of something. It's a delta. And then I see the d, I'm like, derivative, don't know what to do. So that's why I do the delta x and then convert over. Okay, so we'll do this inner integral first. And you might think of like, well, should we have anything in there? Should there be an f of x? But like, no, because all we're doing, the reason we had the f of x before was because we're making a rectangle with the f of x as the height. Now we have our dy as our height. So it's just dx dy. So we'll do the inner portion first, and we get equals integral. That red is a little bit harsher than I like. Should choose a more calming color. Integral of, I'm going to assume there's just 1 in the middle, because you can always multiply by 1. And the integral of 1 is x, and we will evaluate from x initial to x final. Now, we want to get rid of our x's. The idea here is when we integrate by x, we're trying to get rid of the x's. So we want to write this x initial and x final in terms of y. So we have y equals 1/2 x. Well, in that case then, 2y equals x. And if we look at x initial, we're doing it from left to right. So right here, this will be 2y. X initial is 2y. And then x final will be this straight line up and down, which is 2. So we will rewrite this again as integral of x 2y to 2 dy, which equals 2 minus 2y. I'm good with that. Integral dy. Scroll down a little bit. So now if we take the integral of 2 minus 2y, and this is from y initial to y final, we'll have 2y minus 2y squared over 2. That'll cancel out. There'll be some limits of integration here that I haven't yet bothered with. And we will have 2y minus y squared. And now I should probably bother those limits of integration. So y will be from 0 to 1. Now you might be thinking, okay, we want to go from 0 to y equals 1/2 x. Well, that's a good thought, but we've already, I guess, collapsed the x direction. We've already done the integration on the x portion, so we've already taken into account the fact that it's 1/2 x. So the way I think of it is we've kind of removed the x dimension from this, and so we're looking at it without respect to the x dimension anymore. So it'll be 0 to 1. I don't know a really clear way to say that. There's probably some great revolutionary, illuminary type way of being like, well, this is why. But the way I think of it is you're collapsing each dimension until you get a final answer, which is a scalar. So we're looking for a final answer, which is just a number, not x's or y's. And so we collapse the x direction, we collapse the y direction, and then we're left with a number. And that's why we do y from 0 to 1, y initial to y final, and we don't do from like 0 to 1/2 x, because we've already collapsed the x direction. 0 to 1. But if I get the wrong answer, and it doesn't happen to be 1, then we'll start second guessing ourselves. Okay, so we have 2 times 1 minus 1 squared, which is 1. Check. Haha, yes. Okay, so that's the idea behind double integrals. So to backtrack slightly, to find the area under this curve, what we did was integral dx dy from x initial to x final, from y initial to y final. And the point that I'm going to draw attention to here is dx dy. Unlock, delete, okay. And that's the general idea for how you'll find the area under a curve using double integrals. All right, so now let's just talk about the idea behind polar coordinates. So you should already know what polar coordinates are. But the idea here is you have an x and y plane, and you have a point over here, and that looks suspiciously like the graph I just drew. You can describe it in terms of x, y, and x. Or, alternatively, you can explain this point right there, let's call it point P, in terms of theta and r. So, you could say that point P is described in terms of r and theta, or point P is described in terms of x and y, where x and y would relate to r and theta. So to formalize those relations a little bit more, we could say that x equals r cosine of theta, y equals r sine of theta, and then x squared plus y squared equals r squared. Yes. And then you'd also have, in 3 dimensions, you have cylindrical coordinates, which is polar coordinates, but then you have a z value that goes up and down. You have spherical coordinates, which have r, theta, and phi, where you kind of think of, you have the 2 angles describing a direction, and then r then points by how far you go. Then, of course, have x, y, and z can also describe a volume. So it's not that one of these is better than the other. We're generally more comfortable with x, y, and z because that's just kind of the way we build things. We like things to be square, 90-degree angles. Yeah. Most of our things, flat lines work well, which lends itself to x, y, and z, Cartesian coordinates. So that's the idea behind polar coordinates. Now comes a question of, all right, how do we do integration with such. Glad you asked. Just a sec. So let's say we have R1 equals 2. And your first thought is, why is it R1? Is it R2? Yes, there is. Building on this. But start with R1. So radius 1 equals 2. And your second thought is, well, shouldn't there be a theta involved? Yes, I guess so. We'll say theta is between 0 and 2 pi. But it really doesn't matter because theta then just keeps going around in a circle. And this equation here describes a circle. And so let's say we wanted to find the area of this circle. So in case you didn't believe me, let's graph this. Pull up our calculator. Whoop. TI 83 plus. Let's do polar. Polar. Y equals R1 equals 2. Graph. And circle. It looks kind of funny shaped because the screen is funny shaped, but I assure you, circle. Okay. Now that I have won over your confidence, let's integrate this. So your thought process is circle. We'll do double integral dx dy from some beginning x and beginning f, y, beginning y, beginning f. And you can be like, well, let's fill it up with a bunch of squares. True. And actually this would work. Yes, it could work. It's not the most convenient though. And what you want to do is you want to convert dx and dy to d theta, dr and d theta using polar coordinates. Well, oh, did I go back to green? I don't like green. Dx dy equals r dr d theta. So this would equal r dr d theta. And your thought's like, well, where's that second r come from? How do we know this? Etc., etc. Just memorize it. I know that's not the best way to go through life, and doing coordinate basis conversions is actually really important, but it's well beyond the scope of this class. And I'm not even sure if I could even really teach it that well. So, as far as you're concerned, just think that, all right, I have dx dy, it goes to r dr d theta. One of the justifications that you will hear about this is this is more of a mnemonic than an actual proof. You'll be like, well, you have something like this. This is for a small theta here. So you have, on this side, you have delta r. This side, you'll have r d theta, because the length of an arc is the radius times the change in theta. And so it's like, well, this really isn't a square, but it's kind of a square. And so if you multiply this by that, you get r d theta dr, and you can move around the limits of integration, so then you get r dr d theta. That really kind of oversimplifies it. There's a little bit more to it than that, and not really worth you investigating at this time. So for the AP exam, dx dy equals r dr d theta. Memorize it, move on. Okay. So now that we have this, we're doing the inside integration is r, and r is going to go from 0 to 2. It's going to be independent of theta. And then theta is going to go around the circle. So it'll be 0 to 2 pi. So this equals, so the integral of r is r squared over 2. We'll evaluate that from 0 to 2. Okay, and then we'll still have an integral and a d theta. R squared will be 4, yes, over 2, which is 2. So this will give us integral 2. I'm just ignoring the 0 because 0 squared is 0. So I'm not really ignoring it. I'm just knowing that it's worthless to me. 0 to 2 pi. Integral of 2 is 2. So we'll have 2 theta from 0 to 2 pi, which equals 4 pi. So the area of this circle is 4 pi. It's 4 pi. Now let's see if that makes sense. So we have the circle. Despite being off-centered, it's representative. R equals 2. Area of a circle equals pi r squared. I think that's even on your cheat sheet, the formula sheet that you get. You should still know that. So pi times 2 squared equals 4 pi. Nope, that looks like 9 pi. 4 pi. And check. So we have, it seems reasonable that we have our 4 pi here, 4 pi there. This double integral sort of thing seems to work. Okay? Okay? Okay. Okay. So now that we have gone through the basic idea of double integration, and specifically double integration with respect to polar coordinates, let's move on to a more challenging problem, a bigger problem. So we got this, go to that, go with that. We'll assume that's self-explanatory. Nah, I'll leave that up. Nope, I'll put this over with my other stuff. There we go. Okay, so now we have 2 polar coordinates, and we want to find the area between these 2 curves. So first thought is, well, let's sketch it up. Now, let's graph it using a calculator. So this is more difficult than something you'll probably get on the AP exam, but the concept's still good. So we'll work through it a little bit slower than we would if we were just handed this problem to work through. So first, make sure our mode's in polar. Still is in polar. R equals 2. Already up there. Excellent. 3 plus 2 sine of theta. Before, like when I was doing parametrics, I was doing alpha t. T is right there. I was just wasting my time. Wasting my time. Wasting your time. Outrageous. Outrageous. All right, now we probably want to choose our window. 0 to 2 pi is probably pretty good. X minimum. So this is going to be between -2 and 2. This one will be between -5 and 5. Yeah, probably between -5 and 5. And then for the positive direction in the y, it'll probably also be between -5 and 5. So that way we'll estimate a little bit over, do the graph. There's the circle, which looks like an egg, but it's actually a circle. And we got kind of this little lumpity lump. Lisom? I think it means bean, so the top thing looks like a bean. Okay, and we want to find the area in here. So what we're going to do is we're going to find those areas right there. And then, yes. All right, so draw a picture. Drawing pictures. Hop, hop, hop. Purple. Purple picture. So we have, maybe if I do it with multiple colors, it'll be easier. So we have a circle. That is a surprisingly good circle. And then we have a lumpy bean, like so. And the idea is we want to integrate and then find the area in the middle. So first thing we want to do is we want to find these points here, because that'll be our limits of integration for theta. And then we'll do the area of the outside minus the area of the inside. Just like when we have 2 curves and we're trying to find the area between the curves, we'll do the top curve minus the bottom curve. So the way we're going to find this theta is, at this point the two r's are equal because they cross. So we'll set r1 equal to r2, and we get then is 2 equals 3 plus 2 sine theta. So negative 1 equals 2 sine theta. Therefore, sine of theta equals negative 1/2. Okay, so theta equals, so it's going to be the same as, I think it's pi over 6. So this is going to be this angle right there. That was terrible. We're going to be down pi over 6 on this side, down pi over 6 on this side. So, and I'm going to verify that real quick. So the sine of, the arc sine of 1/2 should be pi over 6. Or sine of pi over 6, which is the same as 30 degrees, should be 1/2. Sine of pi over 6 is 1/2. Okay, so yes. Oh. So our theta, so our theta initial will be negative pi over 6, which is this. Yeah, we'll do negative pi over 6. Yes. Theta final equals, I was just wondering if there would be any issues if it's negative pi over 6 versus whatever going all the way around. So it'd be what? 211 pi over 6? I'm going to go with negative pi over 6 though. And we'll go from negative pi over 6 to, I think that both work. It's just the math will probably be simpler if you use a simpler number. And this is pi over here, so that'd be 7 pi over 6. Okay, so now we got our initial and final. Clean up the board a little bit. Oop, there we go. So now we will do, do blue, double integral. dr d theta, and this will be r2 because it's the big one, minus double integral dr1. Oh, we've got the other r, rdr. This is 2, that's 1, d theta. And this would be from 0, because we're going from the beginning, to r2 final. This would be from 0 to r1 final. And then this would be 0 to, not 0 to 2 pi, it would be negative pi over 6 to 7 pi over 6. Okay, so to recap what this is saying is, so this is a double integral, same as dx dy, but we want it in polar coordinates, so it's r d theta. And we want to find the total area of this bean right here, and then we're going to subtract off of it the area from the inner circle. And so we'll find all this area, so from 0, starting from 0 all the way out, minus the circle from 0 to the blue. And we're only going to do the angle where we want the area, because we're just looking for the area in this section here. We don't care about this area here. We could reset things up differently. Like if we wanted to find just the area here, then we could go from 7 pi to negative pi over 6. And then we'd switch the integrals. Okay, so let's see, purple. Do 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 do. Whoop. Okay. Now the question here is going to be, what are 2 final? So our 2 final is going to be 3 plus 2 sine theta. 3 plus 2 sine theta. And our 1 final is going to be 2. Okay. I don't like that squared up there. So now we're left with 3 plus 2 sine of theta squared over 2 minus r1 squared, which is 2 squared over 2. And then I'm going to leave off the zeros because 0 squared over 2 is 0. And these will both be the same limits of integration for theta, so I can then combine them into one integral. And then we'll do from theta initial to theta final, which is just these guys right there. Okay. Hop, hop. A little bit messy. Clean things up. Yeah. No, but I think I'm good for now. Okay. I like how I have a board drawn, like a little box, and then I always go out of it. Don't even, barely even try. Okay, so simplify this real quick. That's 4 over 2, which is 2. So this will be, I'll leave this as 4 over 2. So then this will be 3 times 3, which will be 9. Plus 3 times 2, which is 6, times 2 is 12 sine of theta. This is the FOIL method. Plus 4 sine squared theta. Man, I'll change that to 2. Gosh, so messy. So messy. Over 4 minus 2. This guy right here is actually 2. Change it back to 4 over 2 because I'm indecisive. Still d theta. Okay. Hopefully you followed my mess. Hopefully I followed my mess. We're going to have to get rid of that guy using a double angle formula. Ah, darn you double angles. Okay. So one more simplification and then we will tackle it head on. Whoop. So we have 5 plus 12 sine of theta plus 4 sine squared theta times 1/2 d theta. Okay. Whoop. Go to this. I'll get rid of most of that. Yeah, it's going to go away too. Leave that just so I don't forget. Move this place somewhere more pleasant. Okay. Alright, so now we need to remember our double angle formulas. So we have 2 times cosine of alpha times cosine of Bravo equals cosine of alpha minus Bravo plus cosine of alpha plus Bravo. I guess it's probably more of a beta than a Bravo. Does it matter? Maybe it matters. I don't know. Minus, because when you're using sines, you change the sign. That's just the mnemonic, not actual real justification. And when you have an alpha and a Bravo, or cosine and a sine, then you do sine alpha minus Bravo plus, because it's just like the first one. Okay. So now that I've got my mnemonic done, sine squared will be this one. And so if alpha equals Bravo, A equals B, sine of theta squared equals cosine of alpha minus Bravo is 1. Cosine of 0 is 1. So it'd be 1 minus cosine of 2 theta. And then we have a 1/2 involved. Yes. Okay. So try and get everything kind of in the picture. Dark blue. One too many squiggles on that. 2 plus, so 4 times 1/2 is 2 plus minus 4 times 2 is 2 still, yep. Yep, I'm good with that. Then we simplify things slightly. So the 5 and the 2 becomes a 7. Now, I think we just integrate. So 7, nope. So we'll do, I should zoom in a little bit, there we go. 7 theta plus 12, this is going to be cosine of theta. Now normally, the derivative of sine of theta is positive cosine theta. But we're not doing the derivative, we're doing the integral, so it's going to be backwards. So this is going to be a negative. So if I take the derivative of cosine, we should get negative sine. So we did, yep, so the sign switched. I always get terribly confused on that. The only one I memorize is sine of theta, the derivative of sine of theta. So this is kind of a picture of sine of theta, where I know it crosses the 0 going up like this. And so the mnemonic that I use is the derivative of sine is positive because at 0, at that point, the slope is positive. So that's how I know the derivative of sine is positive, and in fact it is positive cosine. Dark blue still. Okay. Minus 2 sine of 2 theta over 2. Because when you do a substitution, u equals 2 theta. Derivative of 2 theta is 2. And then, so du over 2 is what you'd get. Make sure that most of this is correct. And then make sure that, so here, so this way is the integral, this way is the derivative. So the derivative of sine is positive cosine, so they should have the same sign, which they do. Okay, and then we'll go from negative pi over 6 to 7 pi over 6. And then we'll write out some giant answer. So, clean things up slightly. There we go. There we go. And I'll leave the 2s there. Okay. Purple. 1/2 times 7 pi over 6 minus 12. Now, cosine of pi over 6 is square root of 3 over 2. So we have square root of 3 over 2 minus sine of 2 pi over 6. So 2 pi over 6 equals pi over 3. and sine of pi over 3 equals square root of 3 over 2. Minus 1/2, and we'll do the same thing with, that's supposed to be 7 pi. So this is actually, did I mess something up here? I did. Darn it. Okay, so I'll redo the top portion real quick. So this is so cosine of 7 pi over 6 is square root of 3 over 2, but it's negative, because you think of the unit circle. Negative square root of 3 over 2, which changes the sign. And then we have sine of 2, so it would be 14 pi over 6, which we can take out 12 there. So it's 2 pi over 6, which is pi over 3. So that one stays the same, okay? Minus 1/2. And then this would be negative pi over 6. Whoop, whoop. So we've got 12 minus 12 times cosine of pi over 6, cosine of negative pi over 6, which is the same as cosine of pi over 6, which is square root of 3 over 2, minus sine of 2 theta. So sine of 2 pi over 6, negative pi over 6 would be negative, nope, that's not supposed to be a sine. Sine of negative pi over 3, which will be negative square root of 3 over 2. Plus plus, so we'll distribute the sign here. Negative, no, I'm not going to rewrite this. Oh, am I? Maybe. This is terribly messy. Boom, boom, boom. So, and then we'd go through this, simplify. I'm not going to bother simplifying because this kind of gets the point across already. So, put everything together, and then you get an answer. So to backtrack where this went, so we simplify this, and that's our answer. And the answer we would get then would be the area between this outer shape and this inner shape. And that's the idea of how you would do polar coordinates with integrals in calculus. So your next thought is, wow, what kind of questions am I going to get like this on the AP exam? And you probably won't get ones like this. So we'll go over the kind of style question you're going to get in just a sec. But I kind of want to give you an idea of this is the sort of thing you can see, this is the sort of thing that polar coordinates brings you. Oop. So this is the kind of problem you would be more likely to find on the AP exam. What is the slope of the line tangent to the polar curve r equals 1 plus 2 sine theta at theta equals 0? So there's a couple ways of solving this. I'll first show you the correct way of solving it, and then I'll show you the way that I would probably actually solve it. So there's basically a formula for slope. We have our traditional dy dx. Well, we have x and y here in terms of polar coordinates. So we could find dy d theta, which would equal, let's see, we have to do the product rule on r sine theta right here. So we do have dr d theta times sine theta plus r, and the derivative of sine theta is cosine theta. And then dx d theta equals, let's see, it'd still be dr d theta times, what is this here? R cosine theta, yep, cosine theta, plus r, and the derivative of cosine theta is negative sine theta. So then this would become negative. Putting these together, we have dy d theta over dx d theta equals, multiplied by their reciprocals, times d theta dx, and then do an equal sign down here. Okay, so dy d theta is this one right here. So dr d theta times sine of theta plus, I think that's r cosine theta, r cosine theta over dr d theta times cosine theta minus r sine theta. Okay, so I'll erase this. This is the formula for slope. All right, slope is dy dx for polar coordinates. I would not recommend memorizing this just because there's enough variables in it that it'd be difficult to memorize. If you ever have to know it, I'd recommend using r equals r cosine theta and y equals r sine theta, and then just deriving it the way I did. So you find dx d theta, you find dy d theta, then you take dy d theta divided by dx d theta. Don't forget to do the product rule. And then you get this right here. So in this case then, dr d theta equals, derivative of 1 is 0, and then we have 2 cosine theta, and then we have r at theta equals 0, because we're told theta equals 0, would be 1, because sine of 0 is 0. And so we would be left with 2 cosine theta times sine of theta plus 1 cosine theta all over 2 times cosine, is there 2? 2 dr d theta, 2 cosine theta. Yep, 2 cosine theta times cosine of theta minus 1 sine of theta. Now we're given theta equals 0 here, so that is 0, so this whole part there is 0. This is 1, so this whole part here is 1. These are both 1, and this one is 0. And we're left with 1/2. Okay, which is a possible answer and is the answer. So the answer for this one is 1/2. Now, this is prone to error. You don't have a lot of time, you're under stress to get things done quickly, and deriving the formula and then applying the formula in like 2 minutes? That's a lot to ask for. If you remember the formula, that's possible, but remembering the formula is difficult. So what I would actually do here is just use my calculator. I do, okay, I guess I'd turn it on first. Make sure we're in polar. Delete our previous uses. Oh, come on. I could just hit the clear button. Okay. 1 plus 2 sine theta. And I'll graph this just to get an idea. Okay. Oh, looks like a little, okay. And then we'll do window. And we want it where theta equals 0. So I'm going to leave that as 0. Then I'll do 3.1415 divided by 8. So we're going to go from theta from 0 to 8. And then, let's see, our windows we'll do negative 3 to 3, because 1 plus 2 sine theta can't be bigger than 3, because sine will be at most 1. Yeah, we'll see what happens. Right there. Then we do second, calculate, dy dx, at x equals 0, y equals 0. Sure, see that gives an answer? 0.5. So that says that dy dx equals 0.5, which is the same as 1/2. And so by graphing it and then using your calculator to find the slope for you, granted it said 0.500 something something 8, we'll just ignore the 8 and assume it was actually 1/2. And so what I was able to do in like a minute on the calculator through just sort of winging it took us significantly longer to do by hand. So for this, they give us an equation. It's in polar. So we're like, okay, make sure the mode's in polar, plug in the formula, set the window to be something reasonable so it's easy to kind of see. We graph the equation, and we do second calculate dy dx. Now this is only possible if this is the portion where you'd be allowed to use a calculator. If you can't use a calculator, then you kind of have to do by hand. If you remember the formula or remember how to do the formula, go for it. But if you're stretched for time, jump over to the next one and come back to it when you have time. This is the sort of thing you don't want to get bogged down in. It's really easy to lose track of time. So that is the sort of thing that you'd want to watch out for on the AP exam. So don't get too caught up on just one problem and then miss a whole bunch of easy problems. So this was a lot of material here. It's talked about double integrals, talked about polar coordinates, and kind of how to do integration with such. So this is not really meant to be particularly deep, just kind of giving an overview of, all right, so I get presented a polar problem and which way to stumble forward and hopefully get an answer, maybe even the correct answer. I appreciate your time.